We have to study scattering basically. How we study scattering. But scattering harmony you might have studied in your the way you study classical particles. In the same sense, now you are going to study the quantum mechanical scattering. Because scattering as such, जब आप classical scattering पढ़ रहे थे, whether it was due to elastic collisions or inelastic collisions, in classical particles we had one thing that the trajectory was very much known. ये पता था, there was no cut in between. So you had you know exactly classical trajectory कहाँ से कहाँ तक particles जा रहे थे. But once we enter into quantum particles due to this wave particle duality, तो हमारे पास जो trajectory है, तो we don't say that we cannot talk in that classical sense. अब उसी हिसाब से how we can calculate collisions of particles, whether elastic collisions, inelastic collisions, जो भी हमारे पास हैं processes है. So how we can do the same thing in quantum mechanics, and we can also have what I should say, we can compare classical and quantum what I should say interactions उनकी जो हमारे पास scattering formulas हैं, we can relate the two. And in some cases you should be able to show that classical scattering is a limiting case of quantum mechanical scattering in some coarse-grained approximation. अब for example अगर हमारे पास collision है, two particles का collision है, for example collision or collision or sometimes it's also elastic collision. Then what? How will explain it? For example, if you remember two body problems, हमने वहाँ क्या करते थे? Center of mass, we used to take common and reduced mass. Mu is equal to m1 plus m2 divided by m1 m2, something like that. तो उस हिसाब से we can sometimes make some simplifications. If we take for example scattering angle, हम लेंगे scattering angle is theta, and it's related to angles theta 1 and theta 2. These two particles are coming, they are going to scatter, and the scattering angles are theta 1 and theta 2. So we can relate in the lab system. In the lab system, to study classical mechanics, in the lab system, we can relate angles 1 and 2 as tan theta 1 is equal to m2 sin theta divided by m1 plus m2 cos theta. Where theta 2 is equal to 1 by 2 pi minus theta. Where m1 and m2 are the masses. m1 and m2 are the masses of the two particles. So in case m1 is equal to m2, then we can have a simplification where we can have theta 1 is equal to 1 by 2 theta. You can see it from here. Or we can say that theta 1 plus theta 2 is equal to 1 by 2 pi. This means that if theta 1 plus theta 2 is pi, this means the two particles will, if it's the sum of two scattering angles is pi by 2, it means the two particles after a collision they will diverge at right angles in that sense. अब ये तो classical analogy है, but now we are interested in the quantum mechanical thing. In quantum mechanics, what we are going to say, for example, we are going to say क्योंकि हमारे पास quantum mechanical we represent it by psi. Psi can also be a wave, so you can say जो हमारे पास psi है, psi का as you can write it as e to the power of kx k z can k, because you can say it's moving in the z direction is described by the particle moving the z direction is described by this plane. अब ये हमारे पास है with velocity v. अब जिस तरह हमने कहा था लास्ट वी सेड दैट कोई भी पार्टिकल आ रहा है, इनकमिंग वेव आता है एंड देन स्कैटरिंग वेव आता है. सो हाउ incoming spherical wavefront will also after collision it will interact with the this thing outgoing. So a collision के बाद we can after scattering from very distance the outgoing spherical wave can be f theta equal to k or where f theta is some scattering angle. अब ये है कि और इसको हम you can say that function is also called scattering amplitude in that sense. So at large asymptotic distance जो psi है psi can be approximately एक तो अपना वाला वेव है and plus this scattering wave ये हमारे पास है और so these are two waves which we are going to get in that sense. अब हमारे पास ये है कि we have to see probability per unit time of the scattering particle क्या आएगा हमारे पास probability जो scattering time क्या आएगा for this probability. So what we are going to do is we have to find for example जो हमारे पास scattering cross section है in that sense in a given cross section कितने particles they will enter or leave but that will also depend upon जो angle इनका क्या बनता है in that scattering cross section angle what's that sort of angle which will be there. So we can say that you can say that psi is this where b sigma is basically f of theta. This is scattering angle. So this is d. So this is effective cross section or d sigma is this times this effective cross section जो है इसका solid angle क्या है with respect to this f of theta का क्या है scattering जो scatter करके एक तो अपनी wave है scattered wave में इसका depend करेगा वो scattered cross section क्या है it also depends upon solid take it vis-a-vis solid angle so you can see it this way. So effective cross section हमारे पास DO can be 2 pi sin theta d theta. So d sigma can be written as 2 pi sin theta f of theta d theta. And scattering angle ranges from theta to theta plus d theta. अब ये हमारे पास अब ये है कि if you want to see it through some Schrödinger equation की solution of some Schrödinger equation इसका solution कैसे आएगा how we can see as some solution a part of some Schrödinger equation with energies which we know given by h square k square by 2m उसका orbital angular momentum होगा and various magnitudes in terms of L along some axes. तो हमारे पास जो ये होगा what we are trying to see is that so what we are going to see is that psi हमारे पास आएगा you can say psi where psi is L is to 0 to infinity हमारे पास आएगा. So these are so if you say the wave function का form है जिस तरह हम general श्रोडिंगर इक्वेशन का साइड, इसका रेडियल पार्ट, एंगुलर पार्ट. सो हाउ दिस इवोल्यूशन ऑफ साइन वेव फंक्शन के सॉल्यूशंस हम कैसे निकालते हैं फॉर साइन. तो इट विल फॉर द सॉल्यूशन दिस, so these, you know, these are the Legendre coefficients. This is cos theta and this can be the radial part. So you know how to solve Schrodinger equation for a given sine. Or if where AL are constants and RKL are radial functions satisfying the equation. Hello? Hello? Walaikum Salam. Fifth sheet 90% almost. Oh, yes. तुम्हारा ये तुमका 70%. So you can say it that way. So this is psi L is basically AL cos of sine surface or AL this. So they are the radial functions. तो इसका फॉर्म जो हमारे पास आएगा, it will take this form 1/r square dr r square drkl by dr plus k square minus l into l plus 1 r square. So you know ये हमारे पास it's the typical जो हमारे पास radial solution of a Schrodinger equation, which L and L plus 1 they are the different eigenvalues which we just take for the different eigenstates. It depends L and L plus 1 क्या होगा हमारे पास. अब ये हमारे पास ये है कि in this Schrodinger equation we have sine depending upon A, this is Legendre polynomial and this is a radial part of the equation. So we have to solve this equation. So if you have to solve this equation in that sense, we can for asymptotic solutions this equation इसका equation का form इसमें आएगा and the other part basically we have to solve it for that incoming and the scattering wave जो हमारे पास है. एक तो incoming wave है, एक तो scattering wave है. So we have to see how we can see the incoming scattering wave and the outgoing. तो इनका how we can relate it with the, so ये तो psi है general solution of Schrodinger equation. Now we have to relate it with this the quantum mechanical wave, which not only has an incident thing but scattered particles also. So you have to relate it with this. Take psi is the solution in terms of this. So we have to see this formula and compare it with the original formula जो हमारे पास है and see what will come out to be. So we will see that we can show that for asymptotic this AL जो हमारे पास है इसका solution, remember if it comes from 2L plus 1 iota L exponential of iota del L. So it's coming from previous thing which you might have done if you have studied this book. तो यहाँ से ये आ रहा है. तो अब ये है कि ये जो डेल्टा L है हमारे पास, these are phase shifts of functions or KL. So इसी तरह asymptotic function form of the function or KL इसी तरह एक तो ये है, ये तो AL है. Now the same way RKL can be denoted as approximately 2/r sine of KR minus 1 by 2 L pi plus delta L. So where we get it from previous, once we solve Schrodinger equation, you can see इसका solutions क्या है. Now you can see RL can further be simplified as So if you want to write it in terms of sine, cos, in terms of exponential function, you can also write it as like this. Exponential of iota kr plus delta L minus iota L exponential of kr plus delta L. So we substitute this and this we obtain asymptotic function of the expression for which is an expression. इसका expression जो हमारे पास होगा, you can see it like this. So now you have to substitute this RL and this AL and RK here. एक तो ये है and this one. We substitute this and this equation in this equation. So we get the equation will have the form. It will have the form. It will have the form. हमारे पास आएगा form इसका. Psi is approximately twice everybody sigma L is from 0 to infinity. So 2L plus 1 PL cos theta. Yes. Hello? So it's 2L plus 1 PL is cos theta and minus 1 L plus 1 e to the minus iota k dot r plus SL e to the iota k r. यहाँ पर जो हमारे पास RL का वैल्यू ये आएगा, you see in the book equation 33.20. So वहाँ भी रेडियल फंक्शन का, बट यहाँ पर हमारे पास we have used these expressions. So इसका asymptotic form यही आ रहा है, but it comes from something like this: 2 sine kr minus 1 by 2 pi minus sigma 2 by r. So you have to compare the two functions. Delta L जो हमारे पास इसका फेज आएगा, because you are taking here incoming wave and the scattering wave, उसका solution psi for this thing, psi is equal to जो हमारा इसका solution है psi AL cos theta और k. We are taking psi plus this. You have to see ability. So if you see R को हम ऐसे भी लिख सकते हैं, तो you can say and at the end once you उसका exponential आप करेंगे both sides and there will be some factor of this thing. तो जो equation हमारे पास आएगी it will come psi will be approximately will be equal to 1 by 2 iota k r sigma L is equal to 0 to infinity. 2L plus 1 PL cos theta L plus 1 SL here. So this is psi, the value of psi. We can compare it with the अपना जो previous value. So here this SL comes out to be, so you can write, once you simplify this A1 equation or this radial equation, so this SL can be written as exponential of I2 iota delta L. So if you just compare it with the expansion of how we get the same thing in the previous formula. Previous formula हमारे पास for the same plane wave, it will come out to be, it comes out it comes out the expansion of it comes out to be iota k dot for the same transformation comes out to be iota k dot जो है इसका वेव फॉर्म it will come out to be 0 to infinity 2l plus 1 pl cos theta minus 1 l plus 1 minus k dot r plus k dot r. अब देखो हमारे पास यहाँ पर ये है you have here if you compare this with this last यहाँ भी iota k dot r है यहाँ SL है. SL is exponential of this, so we have an extra factor of this SL as compared to the original when we solve the radial equation of this Schrodinger equation of the form psi is going to be this equation for solution here. But in this altered condition, we got this extra factor of this here. Now we can compare the two, which the extra factor we should arrive at, and the difference can be seen as so f theta. तो यहाँ पर है ना हमारा this is the scattered wave का amplitude हमने निकाला. तो scattered wave का amplitude for the original radial function का form ये आ रहा है. But once we solve it for this, it became with a factor of SL, where SL is equal to this. So f theta scattered amplitude अगर इसका difference लेंगे, f theta minus f theta prime दोनों का difference लेंगे, it will come out to be iota 1 0 2 iota k 2l plus 1 so SL minus 1 PL positive. So this formula solves the expression for static amplitude in terms of delta L, in terms of delta L. अब ये है कि अब we can now integrate it. We can integrate the same function. So this is the thing we have got. Further, if we want to find PL here, PL is the Legendre polynomial and sigma L, sigma को in terms of जो हमने scattering formula हमने scattering formula we are going to take scattering formula. So scattering sigma is equal to 2 pi 0 to pi f of theta square sin theta d theta. We are recalling that Legendre polynomials in different L, Legendre polynomials with different L or orthogonal. Or if we take 0 to pi PL square cos theta sin theta theta is equal to L plus 1. So now what we are going to do, we are going to see psi, जो solution of this thing. So वहाँ पर हमने psi को लिखा था in terms of psi. If I write it psi, इसलिए हमारे पास जो equation है, we have to solve in terms of PL cos theta or PL. So now we can also use Legendre polynomials here. So for solution हमारे पास. So here, so AL निकाला हमने, radial solution भी निकाला, and at the end we are going to see how it comes for the incoming and the scattering period. इसका cross section था, in terms of cross section. पहले इसका in terms of f of theta देखेंगे, f of theta हम नहीं निकाला. f of theta में ही हम इसको PL का वैल्यू मिलेंगे for Schrodinger PL sin theta. So we have to find the total cross section in terms of sigma, and sigma में in terms is f of theta square f of sin theta d theta. f of theta में यहाँ पर हमारे पास Legendre polynomial भी आएगा, SL भी आएगा. So at the end what we are going to see, we have to see the total total scattering cross section sigma. So here it's a bit of work you have to do to catch this value. So it will come out to be L is equal to 0 to infinity 2L plus 1 sin square delta L. अब ये है कि जो दिस थिंग, अब ये जो ओरिजिनल स्कैटर्ड क्रॉस सेक्शन आती है विदाउट दिस फैक्टर ऑफ दिस व्हिच वी हैव टेकन इन कंसीडरेशन, तो उसका फॉर्मूला जो आता है एज अ सॉल्यूशन. So here it's also an exercise how we can once we substitute this we will arrive at this. So I'll just keep this exercise you do at your place how we can arrive at this. The point to mention is that once we do it, the original maximum it comes out to be 4 pi by k square 2L plus 1. So if you compare it with formula, यहाँ से हमको ये आ रहा है for maximum. So if you compare it with the original formula, तो हमारे पास sigma L जो आ रहा है वो आ रहा है 2L plus 1 by R square. तो यहाँ k square जो k can be R, so we can, but the factor of 4 comes extra in that thing. So it's a quantum mechanical result. So normally जो scattering cross section of incoming and outgoing, so it comes out to be this. But once we did this quantum mechanical analysis, taking this and this f theta, इसके साथ, so we get a factor which is 4 times the original formula of scattering which we got. So this is the, you can say it's a purely quantum effect. Due to it's a quantum effect due to scattering, due to scattered and unscattered particles. So this is the result. So we have seen now for incoming and outgoing this thing, scattered wave. If you take this into consideration, so हमारी scattering formula है, get an altered thing 4, and you can take it to this quantum mechanical effect. We can also use idea of partial scattering. Partial scattering को भी हम can also move notions of partial scattering and see partial scattering amplitude for these things. F of theta 12 plus 1, f of L 3L cos theta. So for partial scattering, so it will come out to be again it will be SL minus 1 to 1%. SL minus 1. It will be again, you can do the same formula for partial scattering, and partial scattering cross section can be equal to 4 pi 2L plus 1 f1 square. So they are in partial scattering, they can be related by some phase. So we have arrived at, in today's class, we have arrived at how we can relate the incoming and the scattering waves, taking quantum mechanical scattering and use of psi का जो solution, which is r theta and phi, उसमें Legendre polynomial का बीच में use होता है. How we can relate the two formula and form this formula. And the use of certain phase for incoming, phase factor extra R for incoming and scattering. So we'll stop here.